Okay, now we're recording. Okay. So the key observation we made was, if we know the orientation of the wrist, the posture of the arm gets constrained to a pretty small space, right? And we were saying, look, here are the point clouds. Given a wrist orientation, this red point cloud is where the elbow can be, and the green point cloud is where the wrist can be, right? Just from the orientation. And then we say, okay, orientation is something we know how to measure from our IMU. So perhaps we can do the whole posture of the arm based on this orientation, right? And this is a clear case where human anatomy, human skeleton has somehow constrained the motion of the arm in a way that offers us this advantage that you do not have to track all the 5 variables, right? Even with tracking uh, uh, just the orientation, that itself gives you good amount of information. In other words, the motion model in this case is super valuable. Okay? If the wrist and the elbow and the upper arm could move like one of those straw men, right? Those balloons that they have, in front of some stores where the hands move in all kinds of ways. And if you put a wristwatch on that balloon's wrist, it's very hard to actually track that balloon's arm posture, right? But motion model over here is super important. Okay. So we were discussing last time that, okay, how big is this red point cloud? Because if this red point cloud is big, then the error is large. That means the motion model is not buying you too much. If the red point cloud is small, then the motion model is buying you a lot. And we saw that measurements tell us that on average, the red point cloud is less than 10% of the surface of the sphere on which the elbow can lie, right? The elbow can lie on a sphere around with the center as your shoulder. And given an orientation, the fraction of the sphere on which the elbow can lie is less than 10% on average, right? Of course, there are some cases where it's 50%, right? That on the sphere, there's a 50%, the point cloud is 50% of the area of the sphere. And in that case, tracking, you're not getting so much benefit from motion models, right? So one idea was, okay, if the area of the sphere is not too, if the area of the point cloud is not too large, why not just take the simple average of the point cloud? And yes, you can, and that will give you around a 12 to 13 centimeter of error in terms of your elbow location, which is a 1 feet of error. So even if you move your elbow like that, even if you just don't do anything, just take your motion model, right? Take the center. Just motion model is not good enough. You need to use your IMU to compute the wrist orientation. And from that wrist orientation, compute the red point cloud. And from that point cloud, just take the center of mass of that point cloud, or center of gravity of that point cloud. And that gives you a 12 centimeter of error. But there are some cases, some gestures in which the point cloud is actually very large. And one of the gestures we said was this taekwondo punch, where you move your hand like that and your orientation of your wrist is not really changing. You see that, right? And yet your point cloud of your elbow, the red point cloud, is pretty large because it can be anywhere in that plane, right? So in these kind of cases, if you take just the average, it's not going to work out well. And that is where you want to bring in hidden Markov models. Okay. So the idea is your point cloud, this red point cloud again is the possible locations of your elbow. That is changing as you move your arm, right? These are possible elbow locations. And your job is to figure out where the elbow is at different points in time based on your measurement of your wrist orientation. And if we can do that, this is exactly like how we model the hidden Markov model, then we know the trajectory of the user, of the elbow. Very good. So wrist orientation is the key. From wrist orientation, you can get wrist acceleration. How? Well, you get wrist orientation, you project your local coordinate to global, you do gravity removal, and then you double integrate acceleration, accelerometer, you get wrist acceleration. And for the elbow, you basically do your forearm rotation from your elbow, you do wrist to elbow acceleration, and then you calculate elbow acceleration from your measurement. Don't worry if you don't understand the full details, right? But from your IMU, if you know the wrist, if you can come up with some elbow acceleration, but it will diverge, your red point cloud is going to actually curb the divergence. Great. So now you see where the hidden Markov model comes in, right? You have measured as your arm moves. Let's say you're doing some action and your arm is moving, or let's say you're throwing a basketball and your arm is moving like that, right? Your wrist's rotation is changing, orientation is changing. You have that measurement and you also have the acceleration measurement. But now the hidden Markov model where you are doing probability of M measurement given state, right? That measurement is now acceleration, right? And as a result, you just cannot say measurement given state. I don't know what that is, because given a state, suppose I tell you your wrist is at location XY, what is your acceleration measurement? You say, I don't know. How can I tell acceleration from one location of the state, right? Remember, acceleration is double integration of, acceleration is double differential of location, right? So what you really need is measurement given three states. If I give you the measurement and I say, what is the probability of this measurement given the last three states, then you can say, okay, last three states, I can compute differences of pairwise states. That gives me velocity. And I can compute difference of difference. That gives me acceleration. So from those states, I can compute acceleration, and then I have a measurement of acceleration, and I can say, oh, given that my measurement of acceleration is this, and my states is changing this quickly, I can come up with that probability. Did that make sense? Right? If I tell you the location of a car at the current time, and I say, what do you think is the acceleration of the car? You have no clue. If I tell you two previous points, altogether three locations of the car in time, and now I tell you what is the car's acceleration, you can model what the car's acceleration is. And once you know what the car's acceleration is, and then you can say, does this car's acceleration that I calculated from locations agree with the measurement from the IMU that I have from the car? And this agreement is essentially your probability, right? So now you need to model your hidden Markov model, not just as a function of the current state, right? P of M given S, but we have to model it as a function of the previous states as well. Right? Because your measurement is no longer an instantaneous GPS measurement. Your measurement is now an inertial measurement, which is a function of previous case states. Right? So that's how you model the state. Right? Again, you don't have to do this as part of your MP or anything, but just to get a sense that when it's IMU, you have to model the state variable as the past two states or the past three states. And then once you do that, look, this is how your state looks like. In fact, in this paper, the state is modeled as two locations, which means you know the velocity. And then, so every state is two locations. And then you compute acceleration as a difference between the last two states. So my current state has two locations, the current location and the previous location. That's my current state. My previous state is the previous location and the location previous to that, right? So that's my previous state. And when I do probability of M given S, I would do probability of M given SK minus 1. Probability of M given SK minus 1. And remember, SK is a two-dimensional vector. Sk minus 1 is a two-dimensional vector, and therefore together you can get acceleration. Right? If you had in your IMU, if you had a velocity sensor, then you have two options. One is you can do probability of m given sk, where sk has two variables, two locations, the current one and the past one, right? And the subtraction of those two locations will give you the velocity. Or you could do probability of m given sk minus 1, where sk is a single variable state, but then you're subtracting the current state from the previous state. So you can massage the hidden Markov model to cope with these kind of measurements that are not just a function of the current location, but a function of the previous locations as well.
Professor, so we don't have a velocity, so we just to clarify, our measurement is just acceleration, right?
Yes, our IMU measurements is just acceleration.
Okay.
That is why, at least in this paper, they take each state as two variables, two locations, right? When we did the math, we were taking the state sk as a single dimensional random variable, right? Sk could be sk is equal to L1, L2, L3, L4, L5 all the way till Lr, right? Where L is one location, right? But in this paper, they're saying sk equals Li, Lj. Li could be L1, L2, L3, L4, L5 till Lr. Lj could be L1, L2, L3, L4 till Lr, right? So it's now a vector, right? And now this vector tells you velocity, but it still doesn't tell you acceleration. So you take the previous vector, which is sk minus 1, which is also a two-dimensional vector. And from these two, you can compute acceleration. Okay? So it's a little bit involved, right? It's a little bit involved, but the point is IMU is not a direct function of the location. It's a function of the previous locations, but you can model that inside the hidden Markov model as well. That's the point. Great. And then the rest falls as exactly as it is. You have the transition probabilities, your sk given sk minus 1. That does not change anymore, right? The only thing that changes over there is for sk, you know what that point cloud is. For sk plus 1, you know what the next point cloud is, right? So you can compute the transition probabilities from the two subsequent point clouds. And then you can bring down your, once you combine these two in the hidden Markov model, you can bring it down from 12 centimeter to less than 8 centimeters. So it's not a huge gain, right? It's not a huge gain, but it's still a kind of a 1/3 error removed, right? I mean, from 12 to 8. So that's what you can do, okay? So here is a video of my student Sheng doing this, where he's basically writing ABCD in the air and his IMU is tracking his hand, whereas the red line is from a Kinect. You know, Kinect shines these laser signals and gets the reflection, and it's from a Kinect, and the Kinect and the IMU based tracking agrees reasonably well, which means the IMU tracking is doing quite okay. But the important thing over here is not the difference between the red curve and the blue curve. More importantly, the IMU is not diverging over time, right? In other words, the alphabets are not getting worse and worse and worse over time, simply because your motion model keeps pulling it back into that point cloud, right? You see, right? If you just did this without the motion model, it'll start off nicely with A, and then the B will get distorted, C will get distorted, and by the time you come to G, it'll be really, really bad, right? Going back to our original idea that if you want to walk in a straight line, you will diverge over time and there's no way to correct yourself, right? So this is the basic point. Of course, there are limitations in this paper that you're reading. One of the limitations is that the student had to stand very still and only move the hand. If you start moving your body as well, like you're playing basketball and throwing the ball while your body is moving, very, very hard to track your arm gesture, because your measurement is your arm as well as your body. And the question is, how do you subtract the two? That subtraction is not easy. Okay, so that's one of the key problems, and that's an open problem thus far. There's no work that I know of where someone tries to separate those two. Okay, that's basically what I wanted to say about arm gesture tracking. Let me pause, stop sharing. Any questions thus far? Questions?
Were there pre-notes with this?
Say that again.
I didn't see any pre-notes for this.
Yeah, I did not. I was not able to send out pre-notes. Initially I thought I'll just quickly discuss, but then I kind of today morning I thought, okay, let me start writing, and I did not send out pre-notes. But I think we're already at 11:26, so maybe we will need to do this next class anyway. But let me get started so that you can get started with your thinking process. But I will post the pre-notes for next class. So maybe the first 15 minutes of next class, we will again quickly talk about particle filters and then move on. But for today, let me just introduce the motivation and the idea to you. Okay, good. So we are finishing up hidden Markov models. We saw one application is in autocorrect. You remember this one. We saw this other application in arm gesture tracking, where the motion model comes from the locations that the elbow and the wrist can take, the point clouds. Okay, and all of these we have used hidden Markov models. Okay, so if you think of hidden Markov models, hidden Markov models have been shown to be optimal, meaning that every piece of information is being used and every trajectory that is possible is being tracked. Okay. Now, there are various follow-up works after hidden Markov models where you want to make things more general, where you want to relax certain assumptions and so forth. So we want to revisit hidden Markov model and see where things can be made better for hidden Markov models. Okay, so here are some. First is, thus far we use hidden Markov models, which is really in discrete space. Right? We said that the robot's location, we always have this picture in our mind. We always have this picture in our mind. And this picture essentially says location is L1, L2, L3, all the way till LR. So location is discretized. Right? It's like tiled, and as if the robot is moving from one tile to the next tile or moving back or whatever. Right? Real world is not really like that, right? In real world is continuous, right? So most of the real world applications is in continuous space. So we need to be able to bring HMM or bring these kind of Bayesian inference. HMM is the broader term for HMM is Bayesian inference. You're inferring where the user's location is using Bayesian logic, right? This given that, that's Bayesian, probability of A given B. So we want to bring Bayesian inference to continuous space applications. HMMs do not tell us how to do that. Number two, HMMs need transition probability matrix as motion models. Right? We always want this value P of Sk given Sk minus 1. Right? If I tell you, okay, for a self-driving car, what is that motion model? It would be a little bit of a pain to compute that transition probability matrix, because all you really know is that the car would go at some speed limit. The car might accelerate if there are no other cars in front. If there are a lot of cars in front of you, it might decelerate. So we want to kind of make this notion of probability matrix a little bit more general so we can accommodate other mobility models as well. Right? So for example, I might know velocity and acceleration distributions of a car, right? I know that the distribution of the velocity of this car is it is a median around 70 miles per hour with maybe it's a Gaussian distribution on the highway. It's a Gaussian distribution with a median of 70 miles per hour and a variance of 10 miles per hour. That's a motion model too. That doesn't tell me what the probability matrix is, but that's a motion model, right? So more generally, I can say I have Sk, which is a function of Sk minus 1. And I want to be able to design Bayesian inference for any given function G. Right? That's a nice relaxation, generalization of hidden Markov models. Another point is HMMs thus far have not modeled noise. But in reality, any measurement will have noise. Your state transition diagram, your state transition probability may not be accurate. It might be noisy. So in general, you want your measurement to be some function of the state plus noise, and your state transition to be some function of the previous state plus noise. Right? So now we are kind of thinking, where all can we generalize things so that if we can come up with a general model, it can apply to any applications that is thrown to us. Okay? And finally, computation cost of HMM is pretty high, right? Why? Because remember, you're tracking every possible path, regardless of whether the path's probability is high or low. Right? Even the most unlikely path you will track, which means your computation is really, really high. But if someone says, look, you have to run this on a mobile phone, you realize that, hey, there are these very unlikely trajectories that I'm tracking. Maybe I should not track all those, eliminate those. I only track the probable trajectories. Right? So that gives you opportunity to cut back on computation. I want this general Bayesian inference model or general Bayesian inference technique to have all these properties where I can scale up and scale down the accuracy of the tracking based on how much computation power I have. Okay. So this is where particle filter becomes interesting, where it kind of generalizes HMMs in the following way. It can be continuous space. It can be any function of f, any function f and g, where f was essentially the function of measurement and g is the function of motion model or any state transition model. And it can accommodate any noise. And it can reduce computation as necessary, of course, with a trade-off that your accuracy of tracking will go down. But it'll go down not dramatically, it'll go down optimally. It'll go down a little bit, and yet you'll gain quite a lot in your CPU computation. Okay. So I'll just briefly, in 2 minutes, I'll tell you what the core idea is so that the seed is planted in your mind. And as you think about it, next class we'll come and make it cleaner. Okay. So the basic idea is the following. Again, it'll be high level. But we'll say, look, initially, we had that robot going from one location to another like this, but we don't want that space to be discrete anymore. We will make it continuous. So we will say we have a velocity distribution, let's say, that looks like that. This is the velocity distribution of the robot. Which means what? This is the most likely velocity. This velocity is low probability. This velocity is very low probability. Or the robot going from, actually, maybe I should not bring the velocity distribution here. Let's say there is some velocity distribution, which is like this. This is 70 miles per hour. Right? Great. Let's keep it over there. That's the velocity distribution. Okay. Now in continuous space, what I'm going to do, okay, actually let me pull back and let me say this. The core idea with particle filter is that I am going to model my belief with a particle. What does that mean? It means if I put a particle here, you can think of particle as probability mass, but let's call it particle right now. If I put a particle here, it means I believe the robot is here. If I put a particle here, then this particle and this particle together has the same probability mass. So I would believe, let's say this is half and this is half, then I believe with half probability the robot is here, and with another half probability the robot is here. I could change my belief by saying, you know what, I believe with 7/10 probability that the particle is here and 3/10 probability that the particle is here. Okay. So initially, maybe I do not know where the robot is. So I'm going to put maybe n particles with equal probability at different locations. I will spread it across the entire space of possibilities. So I have n particles and I spread it across all the possible locations in which robot can be. Okay. And then I say each particle will propagate, will move based on this velocity distribution. So I take this particle, I take this particle and I say this particle will have some velocity that is sampled from this distribution, let's say 56 miles per hour. If it has 56 miles per hour, it will move over here. So I bring that particle over here. Similarly, I bring this particle maybe at 72 miles per hour over here. I bring this particle here. I bring this particle here, and so forth. So at the second time instant, I have here, 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 here. Okay. And now I make a measurement and I ask if the particle is here, if the particle is here, how well is the measurement agreeing with that hypothesis? Right? So I have a measurement error and I multiply that probability to this particle. So after I have propagated the velocity with this velocity distribution and then done a measurement, meaning after I have done Pm given S, and I've also done Psk given Sk minus 1. This is basically from the velocity distribution. And this is from the measurement. Now I have different particles with different weights. Does that make sense? Why different particles are getting different weights? Because the particle which moved forward with a velocity close to the mean has a higher weight because the probability is higher. And the particle whose location agrees well with the measurement also gets an additional weight. So some particles get a higher weight, some particles get lower weight. So this is a particle with high weight, maybe high weight, and these particles are with lower weight, and the later particles are with lower and lower weight. This is what I started off with beliefs where all my beliefs were of equal weight but scattered. but now my beliefs have kind of concentrated on this area, and my belief around this area has become smaller, right? So now what I do is I say, look, I have only n particles. These beliefs are not that useful because they're already very low. Let me bring these particles back to the region where my belief is high. So I basically take these particles, I delete them. Sorry. I delete these particles. And I bring them back over here. And I put those deleted particles back into the locations of the other particles where the belief or the weight of the particle is larger. So what am I doing really? Remember in the previous one where this was time t1, t2, t3, so on till tn, and this was location L1, L2 till LR. Remember, right? The trajectories were like this. And suppose this is a very low probability trajectory. And you know that it's low probability even here, because even at this point, you know that the probabilities have already become very small. But you still keep tracking that in HMMs. In particle filter, you're saying, hey, let's eliminate this. Maybe there is another low probability part trajectory. We say, hey, let's eliminate these and only track these higher probability trajectories. Okay, and we are going to do this by putting the particles in place where my belief is, right? And whenever the particles get scattered in with low belief, we are going to kill those particles and bring those particles back into places where my belief is high. And as a result, at any iteration, the computation I make is order of n, right? Because the number of particles is remaining the same. It's just that I'm always concentrating my particles along the trajectories that are likely.
Have a short question.
Yes.
Is it just a beam search on top of HMM?
It's a beam search, but there are slight differences. These functions can be non-linear, and there is a way of what is called importance sampling, where beam search is only going to search. Over here, you have this control method where you're actually moving the particles into the place where it's really high density. So in beam search, you will essentially say, oh, I don't need to search this part, but you're not going to change anything over here. But in particle filter, you're saying, oh, look, these particles over here, you need to bring these particles back into this region. And now when you bring these particles back into this region, where do you put these particles? You've killed these particles, but where do you put them? Oh, you distribute them in proportion to the weights of these particles, right? So suppose you've killed 5 particles over here, 5. Where do you put them over here? Oh, what you do is you put 2 particles here, maybe 1 particle here, 1 particle here, and 1 particle here. But you put 2 particles here because that location, you have had more belief associated to it, right? So the killed particles get distributed in this region in proportion to the probabilities or the weights of the existing particles in that region. So that part is where it differs from beam search. Beam search is only saying, let's eliminate and keep moving forward. Jia Hong, that does make sense?
Yeah, that makes sense.
Okay, so we'll stop here, but we will make this cleaner next time. But I wanted to plant that seed that now think of your state as a particle, and you have some belief associated to that state. And these particles are now moving. These particles are like clones of the robot, right? Every particle is a clone of the robot, but that clone of the robot has a weight associated to it, and lower the weight, less is your belief that the robot is there. So you kill that clone, which is a low probability clone, and you bring that clone back to where the probability of that clone is high. So the clones always concentrate in locations where your belief is stronger, and then you propagate again. Okay? So we will talk about this, and we'll connect this to Kalman filter, where we'll say that, oh, when F and G are linear and noise is Gaussian, that's when it becomes a Kalman filter. Okay, so let's pick up from here next class, and I'll see you on Wednesday. Okay. I'll hang back over here if you have questions, but thanks for coming in and thanks for attending the seminar.
Thank you.
Thanks.
Professor, for the bottom diagram, so like with sort of this idea of readjusting the particles instead of just killing them off. So you can sort of visualize that in the bottom diagram as deleting the low probability sort of trajectories and then
Exactly.
drawing them along high probability ones. Is that sort of a way of visualizing?
Correct. Yeah, exactly. You can,
Okay.
you're basically killing this trajectory over here, right?
Mm-hmm.
Instead, you say, look, whatever I was going to do over here, basically follow that. Instead, I'm going to put my computation in looking at all various possible trajectories from here. So this
I see.
particle would have, the particle that would have followed this trajectory, you're saying no need to do that. Might as well that particle you bring over here, over here, because this is the same time, right? You kill the
Right.
particle over here and you bring that particle over here, and that particle follows this trajectory from here, right? So all the particles that you're killing, you're bringing them here so that from this location, from this state, each of those particles can trace different possibilities.
Got it. Okay, cool.
And that's because you want this this probability is high, so you better put all your bets on along that direction.
Right. Okay, cool. Thank you.
Thanks.
Have a good one.
You too. Thanks.